So we are now going to look at reminding ourselves of what different set notation looks like in a question, moving then on to conditional probability, which you actually have met before. It's just that we're looking at it in a different context to how we've previously seen it, and then moving on to conditional probability with Venn diagrams before we look at specific formula that you need to know, and probability trees. So the majority of this is actually a repetition of GCSE, which is why this chapter is really, really nice, I think, and can be done quite quickly. So a card is selected at random from a standard pack of 52 playing cards. So it is expected that you do know how a pack of cards is made up. So as an OLA that I might give you over the Easter holidays, especially because we are stuck inside, and knowing April and knowing Easter, it's going to start raining and it's going to be really miserable when we actually just want to spend time in our garden. Get yourself a pack of playing cards and learn how to play games of cards. So play with siblings, play with parents, guardians. If you have siblings back from university, it's a really nice bonding game. It's just a really nice family game, and there's lots of games that you can play on your own as well. So I will put up some suggestions of what I think are really good games. I am a card game player. I really do enjoy it. My fiance and I tend to play a game called Crib or Cribbage. So that's a really good one that you can play just with one other person, or you can actually play with a small group. So that, I think, will be a nice OLA for me to set you for some family time, really, as much as anything else. Because obviously during these times, that kind of thing is really needed. In case you don't know, there are 13 cards in each suit, and we have our red cards, which are hearts and diamonds, and our black cards, which are clubs, which I almost forgot how to draw, and spades. That's a really rubbish spade. It looks more like a little duck, but you catch my drift. So there are 13 of each suit, and in every single suit you have a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, a 10. You then have the picture cards, which are Jack, Queen and King, and then you have an ace. Ace, just in case you want to know, can be played either low or high, depending on what you need it for. Quite often a lot of games play it as high rather than as 1. Crib uses it as 1 actually, but it is just something that is useful for you to know. So there's 4 of every single one of these across the whole cards. So in this example, let event A be the event that a card is a queen, and event B be that it is a black card. So before I answered this, I would draw my Venn diagram. It's only event A and event B. So A is a queen, B is a black card. Let's do the intersection first. So there's 2 black suits and there's a queen in each one. So there's 2 cards that are queen and black. There are in total 4 queens, 2 red and 2 black. So there must be 2 that are not black cards that are also queens. There are 26 black cards because there's 13 in each suit. So there's 13 in this suit and 13 in this suit. So there are 24 that are black only but are not also a queen. This in total has got to be 52. So here we've got 28. I really can't be bothered to use my brain right now. So there's 24 cards that are not either a queen or a black card. Always check that your thing adds up to 52 because this is obviously our universal set. Okay. So, find the probability A intersection B. So that's the probability that both A and B occur. So I was looking at this section, which is 2 out of 52, or 1 out of 26. B, find the probability of A complement. So A complement means not A. So that's everything except for this circle. So it's the 24 and the 24. So not A is 48 out of 52, which is 12 out of 13. C, probability of A union B. That's everything inside these two circles. So that's 28 out of 52, which is 7 out of 13. D is the probability of A complement intersection B. So that's not A, but also B must occur. So A cannot happen, so we're not looking inside this circle at all. But B must happen, so we are only looking at that value, which is 24 out of 52, which is 6 out of 13. And finally, I'm going to use my green. I did actually like my green. The probability of A complement union B. So that means either A does not happen or B does. So the only place that we're not looking is that A definitely happens, because within this circle, B happens, and here, A doesn't happen. So it's 50 out of 52, which is 24 out of 25. So really, really quite straightforward. So that's my first example. So I'm going to go on to my second example, which is in a more exam style question. So given that the probability of A is 0.3, the probability of B is 0.4, and the probability of A intersection B is 0.25, explain why events A and B are not independent. Well, the rule for independence, I can't remember. Independence, whichever it is. I would check my phone, but my phone is recording. Ignore my dodgy spelling. We are, what, day 9 in self-isolation? Something like that, when I'm recording this. So I'm not really necessarily thinking as straight as I should be. I can teach you mathematically, but my spelling's out the window, so I apologise. It's on my PowerPoint. Independence, there we go. If independent, not independent, so for goodness sake, I'm just going to scribble this bit out again. If independent, then I know that the probability of A multiplied by the probability of B is the same as the probability of them both happening. So I know that to be true. If we think about probability tree diagrams, events on different branches are independent, and we multiply them to find the probability of them both happening. So 0.3 times 0.4 is equal to 0.12. 0.12 is not the same as 0.25. Therefore, they are not independent. Now, you can't say they are dependent. Dependence is not the same as not independent, okay? it might be that there's a third factor, so we do have to be careful with our language, so it's not independent. Given also that the probability of C is 0.2, that events A and C are mutually exclusive, and that events B and C are independent, draw a Venn diagram to illustrate those three probabilities. So lift it up a little bit more. So, A and C are mutually exclusive, which means that A and C do not overlap. So it's going to look something like this. Well, I know that A intersection B is 0.25. The probability of A is 0.3. So therefore, the probability of A completely on its own, not including B, must be 0.5. I know that B and C are independent. So therefore, the probability of B times by the probability of C must be the probability of their intersection, which is 0.08. So the probability of C is 0.2, take away 0.08 is 0.12. The probability of B is 0.4, so I'm going to take away 0.25 and take away 0.08, which is 0.07. I have to have my probabilities add up to 1 because this is my universal set. So I need the probability of none of those happening. So I'm just going to add together all the probabilities that are written in my diagram, which is 0.57. So therefore, the probability of none of those things occurring is 0.43. C. Find the probability of A intersection B complement or C. So in the exam they might use square brackets or they might not use brackets, so you just have to be careful with the notation. So just be aware that clearly this has to happen as a precedent to this. So A intersection B dash. So that means A happens and B does not happen. So that means we're looking at that section there. Or C happens. So that means we're looking at all of C. So this is separate to this. So A and not B, which means that we're looking within A, but we're only looking in the section where B doesn't happen. Or C could happen. That means we can look at this bit where B happens. So we've got 0.2 and 0.05. So it's 0.25. So that's why shading on your Venn diagram is also really helpful. So that's just a quick revision, or fairly quick revision of set notation, being able to understand the written probability. So we are now going to move on to conditional probability. So this is where we know a particular event has happened. So the probability of one thing happening, in this case, is dependent upon another event occurring. So we have the information given that something else has already happened. What's the likelihood that this happens? So at GCSE you might have looked at 2A table questions, and it might be that given the student you pick as a girl, what's the probability that she has blue eyes? So you're looking at the likelihood of someone having blue eyes out of the likelihood that they're a female. So let's say there are 20 females, rather than out of the total 50 students, it's only going to be the number of blue eyes out of 20, not the number of blue eyes out of 50. So that's where the probability changes. Now the way that we write conditional probability is like this. So this is the probability that B occurs given that A has already occurred. So this means B given A. So the probability that B occurs given that A has already occurred. Now we can use this for independent events as well. So a new rule for independence, because if they are independent, then the probability of one happening already shouldn't impact the probability of the other. So the probability of B given A is just the probability that B happens, because it shouldn't impact each other. There should be no impact. That also means that the probability of of B given that A hasn't happened is also just the probability of B, because they shouldn't impact each other at all. So we can use this rule as well to determine independence. So we're going to look at a couple of examples of conditional probability. So a school has 75 students in year 12. Of these students, 25 study only humanities and 37 study only science. 11 students study both science and humanities. Draw a two-way table to show this information. So, we've got humanities or science, or we've got not humanities. Humanities or not humanities, and we've got science or not science. Sorry, that makes more sense. Because either they choose humanities, or they choose a science, or they choose one or the other, or both. And then these rows are our totals. There. Obviously, it's a very scrappy table, but it would do. So humanities or not humanities, science or not science. So we know there are 75 students in year 12. 25 study only humanities. So that means they study humanities and not science. 37 study only science. So that means science and not humanities is 37. 11 study both science and humanities. So that's yes science and yes humanities. And we need to make this add up to 75. So 75, take away 37, take away 11, take away 25. So 2 study neither. And for completeness, we do want to add up our tables like that. Okay? Find the probability of that they don't study science and they also don't study humanities. So they are these 2 students. So it's 2 out of 75 because they don't study science and they don't study humanities. B part 2. Find the probability that they study science given that they study humanities. So the total students that study humanities is here, not there. That's me reading my table wrong. I was looking at total science. So I know that this student studies humanities. So it's out of 36 students. I want to know the likelihood they also study science, which is 11. So the likelihood of picking someone that studies science given that I know they study humanities, is 11 out of 36, because I'm only looking at the 36 humanities students. Part 3, the probability they study humanities given that they don't study science. So there are 27 students that don't study science, so I'm picking from those 27 students, and 25 of those do study humanities. So the likelihood of getting someone that studies humanities, given they don't study science, is 25 out of 27. Second example. 2 four-sided dice are thrown together and the sum of the numbers shown is recorded. Draw a sample space diagram showing the possible outcomes. So sometimes they will want you to draw a sample space diagram. I expect most of the time they won't actually ask you. It just might be useful for you to work out probabilities. So they're four-sided dice. It doesn't say, but you can assume, or you should assume, they are the numbers 1, 2, 3 and 4. Because there's no other assumption really to make, and actually the question does ask you about your assumptions later. So you want the sum of the numbers recorded. So 1 add 1, oh, let's fill it in with a colour, because I can. Oh no, I've dropped my black pen on the floor, it'll be fine. 2, 3, 4, 5, 3, 4, 5, 6, 4, 5, 6, 7, 5, 6, 7, 8. So that is the score of each of the dice added together. Given that at least one dice lands on a 3, find the probability that the sum on the dice is exactly 5. So given that I know it's landed on a 3, what's the probability that the sum is 5? So I'm looking at all of the options where one of the dice has landed on a 3. So there are only 7 options where the dice has landed on a 3. And the likelihood of it being a 5 as the sum are 2 options out of 7. So drawing a sample space diagram is really, really helpful in this case. State one modelling assumption you used in your calculation. So we assumed that both dice were fair, and we assumed that both dice had the numbers 1 to 4 on them. So they are the 2 modelling assumptions that we've made. You would just name one of them. In particular, I think they're talking about the 1 to 4, but assuming it's fair is a really big assumption that we have made, and it's a really important assumption because we are assuming that every single one of these 16 outcomes has an equally likely chance of happening.